Coming down to it, and I'm going to start talking about a new topic, but we're going to connect things up as usual. So Sedona sets. So this is theory of Sedona sets was developed in the 1950s. That's the theme of this this course. The golden age. We're going to talk about the beautiful work of Walter Rudin. And but we got to go a little bit back to Sedona himself. He was a little bit older. So Sedona in 1927 proved the following result: that if I had a continuous function on the circle, which is what they call which has a lacunary trigonometric series. So that means suppose that the Fourier coefficients are always 0 for every n, not n lacunary, the powers of 2, but more generally, we take a lacunary sequence of integers. So that's what we call a lacunary Fourier series. So when I expand the Fourier series, only powers of 2 to the k appear. And he observed that whenever this happens, then automatically the function has an absolute convolutional Fourier series. That was a very nice observation of Sedona, but it was kind of an isolated result. Okay, people knew about it, appeared in the first edition of Zygmund's trigonometric series book, but it was really Walter Rudin that sort of understood how to take this isolated result and make an entire theory out of it. So this is how his mind works. He's done this on a number of different problems, but this is Rudin. We're going now back to the 1950s. And he realizes that to think about any set, just not this sequence, sparse sequence of integers, but he made a definition he called a set E of integers is Sedona if you look at all continuous functions. So I'm going to define for you a Banach space. This is a closed subspace of continuous functions under the uniform norm, L infinity norm. I'm going to look at those continuous functions whose coefficients vanish for all n, not in the set E. So that just means I'm looking at continuous functions that are Fourier supported along this set of frequencies. And he calls it and so this you can check, it's the closed subspace, and this is the Banach space under the L infinity norm. And if this is automatically, this is contained in any such function automatically as an absolute convergent Fourier series. Okay. That's what he calls the Sedona set. And of course, Sedona, let's just note a number of things. For instance, Sedona himself said that a lacunary sequence is a Sedona set. Or in general, you get 3 to the k, or you can have any sequence of the ratio of 2 consecutive sequences uniformly bounded away from 1. So these are sparse by its nature. They're sparse sets. Let me mention here that in fact this is Rudin's observations is that Sedona sets have very interesting arithmetic properties. For instance, lacunary series, you can easily check. They cannot have their integers cannot be represented as sums of lacunary numbers. Not so you don't have that many representations. But in general, the Sedona set, this is all observations of Rudin from the very famous paper from the 1950s, trigonometric series with gaps. Beautiful, beautiful read, beautiful paper, and he outlined this theory and showed what kind of arithmetic properties you have. So you can quantify the number of representations given a Sedona set E, then you want to quantify the number of representations. I can write an integer as a sum of k elements, all of which are in the Sedona set Okay, and you get bounds for this number and so on. So the final observation I just want to make here is that this actually, again, going back, I'm going to probably don't want to really go in this direction, but you can make this, this problem makes sense in a very wide setting of any locally compact abelian group. So I take a compact group, okay, so the locally compact abelian group, okay, that means that the dual group is discrete. Okay, we're thinking about G being the circle group, compact, the dual group is the integers, and then we can talk about a Sedon set and the setting any Sedon set in the dual group here. So this is a discrete sequence of points, if you like. This is Sedon. So everything makes sense here. If I look at the continuous functions on the group itself. Okay, so that means it's Fourier supported in the set E. Automatically, it's in the Fourier algebra of G. Okay, so all of this, at least for compact, locally compact abelian groups, this notion of Sedon set makes sense. And I can talk, and again, Walter Rudin, first of all, developed all these properties for subsets of the integers, and then he went on to develop the theory in general, compact, locally compact abelian groups. Right, okay. So this is Rudin's program that he outlined. He's trying to characterize Sedon sets purely in terms of their arithmetic properties. And he sort of gave a guide. He actually showed exactly what he meant by that, and because he had all of these lemmas. If the set is a Sedon set, then it has these various arithmetic properties. And can you actually, in some sense, do these properties characterize when it's Sedon? So what he did was, so that was his big program that he laid out. It was an important program. It caught the attention. A lot of people started in the 1950s, and it wasn't solved until the 1980s. And it's a beautiful solution. So people like Bourgain was very interested in these things, and eventually it was solved. But before that, I want to give the key. So this is a proposition that was proved by Rudin himself. So Rudin proved that, in fact, okay, in this generality, he first did it for the circle group. So I take a compact group, and if he showed, if E is, which is a subset of the discrete group, G is Sedon, then he proved that I take any function in a certain function space, and so this is, you can't do this for L1 functions, but you get very, very close to L1. And you take any function in what's called the ordered space L square root log L. And you take that function and you look at its Fourier transform. Now on the discrete group, I take the little L2 norm of this, I restrict it, sorry, and then I restrict it to E, my limit is at E. I can control that by an absolute constant, uniform constant times the L square root log L of a function on the compact group. Okay. And that's sort of an endpoint. So you certainly cannot do this for functions in L1. Okay, so this was because in L1 function, we know that the Fourier coefficients, just think of L1 on the circle, the Fourier coefficients, although they go to zero, they can go to zero arbitrarily slowly. And in particular, when you restrict them to 2 to the k, for instance, a Sedon set, it's not going to be square summable. Okay. So it was an observation of Paley that nevertheless, if you had an LP function on the circle for p strictly bigger than 1, It is true that I can restrict its Fourier coefficients to a Lacaniere series, and it's summable. Okay. And then it was an observation, and then it was a theorem of Zygmund. Now we're going back to the 1930s that actually showed this. Maybe I'll give this a name star. So star holds for Lacaniere sequence. Powers of Tuesday. So this is, now I'm in the setting of the circle group. I take this particular sparse sequence of Lacaniere, Sidon, before Zygmund showed that in fact they have this property that any such function that's Fourier supported in these frequencies automatically has an absolutely continuous convergence Fourier series, and in some sense by duality, Zygmund refined this. All these observations of Pele, he refined this. Of course, you cannot show this is true in L1, but he showed that this is the endpoint space that you can do the same. And in a way, so what Rooted did, he just upgraded Zygmund's result for a general Sidon set on the first of all, he did this for the circle group. So for a general Sidon set on a circle group, you have this inequality, and then in a later paper, he generalized this to a general compact group. And this turned out to be the key. So this is what Walter pointed to. This is sort of the key analytic. If you can show that this in fact characterizes, and it's an inequality, characterizes Sidon sets, then that unlocks the arithmetic characterization of Sidon sets. Okay, so maybe I'll make this.
What is that? What is that L on the star?
What is A?
L. Norm of a L dot
L square root log L. Okay, have you ever heard of the space L log L, these Orlich spaces? So instead of taking a function and taking the p's power and saying that is, I could take other functions like t to the p. I could take my function f of x to the p. I'm taking t square root log t. I'm putting my function in absolute values inside there and ask that to be integrable. That's kind of, there's not exactly a precise definition. That's kind of what I mean. Okay, so that is something that's lying between L1 and LP for any p bigger than 1. Okay. Right. So this proposition, did I say it was a proposition? Did I call it? Yes, I said it's a proposition of the Walter Rudin. So the proposition, what's well known to Rudin anyway, is the key analytic to unlocking the arithmetic characterization of Sidon sets. Okay, so if we could actually somehow show that that's an if and only if statement. And this was the nice, so this is eventually we have the big theorem here due to PCA. There's another proof due to Organ later. But PCA showed that in fact the set take a compact group and I look at a subset in the dual group. This is Sidon, if and only if. Stop this. Or E. So we know by Walter Rudin that if it is a Sidon set, then this then I can always control the restriction of the Fourier coefficients to this set in little L2, at least in the space of L square root log L. And so PCA said, suppose I had a set E that satisfies that inequality star, then it has to be a Sidon set. Okay. That's a very nice, another example of how we start with a very simple result of Sidon that goes back to the 20s. very concrete result, and how one develops a beautiful theory. This is the way that Walter Rudin thinks. Okay, and then we eventually came to this wonderful result of PZA. Right, now, again, like before, so we had this result, this Helson-Berling result, or if you like, this Leibniz-Kahan result that we started with, and then Kahan himself relaxed, had a variant of this result. We're going to look at a variant of this. Okay, Sidon says this. So this is due to Ilianov. In about 1954, he wrote a paper introducing, again, we're going to just concentrate on now spectral sets of integers. This is, by definition, this is a definition now. This is a UC set. So UC stands for uniform convergence instead of a Fourier series with an absolute convergent Fourier series. So is a UC set if I take any continuous function that is Fourier supported in the spectral set, instead of requiring that automatically has an absolute convergent Fourier series, I'm just going to require that automatically means it has a uniform convergent Fourier series. Again, we relax the condition of absolute convergence for the Fourier series to a uniform convergence of the Fourier series. Right, okay, so note, of course, this is all Sidon sets, of course. Are UC sets, right? Because we have all Sidon set by definition automatically has an absolute convergent Fourier series and therefore automatically has a uniformly convergent Fourier series. Now, but Sidon sets are very sparse by nature. Okay, so they have very small density. You can quantify that as part of this whole program of understanding, characterizing what Sidon sets are. Okay, and now the question is, the basic fundamental question is, when I relax this, could these sets be much denser or not? And so first of all, is there an example of a UC set, a set of uniform convergence that is not a Sidon set? And that was an example that was given by Figure Talamanca back in the 50s, I think. So do we have any Italian in the audience? I think they're all A's. Talamanca, is that right? We show that this, if you take some sense, lacunary. So, okay, you have a lacunary that's a Sidon set, then this is a uniform set of uniform convergence, but not well known that when you start taking some sets, you make things a bit denser, it is not Sidon. Okay, so we can get things a little bit denser by taking subsets. Okay, so we have this very thin sequence of the lacunary sequence. I take subsets, I get something slightly more dense, and I still am in the world of uniformly convergent Fourier series. And the basic fundamental problem here, and this was posed by Ilianov himself. And so this is the fundamental problem, because we really didn't understand if I could get anything denser than these sum sets. The question is, can they be, how dense can they be? And Ilianov himself asked, can it, for instance, is the squares? So let me denote as B, as square just to be squares, integers. Okay. So is this a uniformly convergent set? That was the problem. Not so easy, it turns out. Okay, that was posed in the mid-1950s by Ilianov, and it wasn't solved until the late 1980s. And so the answer turns out to be no. No. Okay, this is proved by Arkhipov and Skolkov. 1988. Okay, no, it can't be that dense. Okay, so in other words, there exist continuous functions. There exist continuous functions that is Fourier supported just in the squares, and does not have a uniformly convergent Fourier series. Okay, so let's Let me give a definition. Let's see how we're going to attack this problem. How do we even start to think about it? So let me define some numbers. These are important numbers. I take any subset of the integers. So I take a sequence, and let's define what are called the Lebesgue constants. So with respect to the set E, I'm going to generate a bunch of numbers, and these are just by definition. Let me write out the definition. I'm going to compute I'm going to take the Fourier partial sums of order n, compute their L infinity norm, and to take the supremum of all continuous functions that are Fourier supported, and use L infinity norm examples for 1. Okay, so all I'm doing here is I'm just looking at this guy. I take this is a mapping from continuous functions to continuous functions when I just project it down on the first n frequencies, but it also preserves the space. So I can think of this as a bounded linear operator on this closed subspace of continuous functions that are Fourier supported. The linear operator, and this is just computing the operator one. This guy is just the operator one of this operator there. Okay. These are very important numbers in approximation theory. These are the Lebesgue constants, called the Lebesgue constants. And they're notoriously hard to compute of my set E. Okay, of course, in the setting where E is everything, it's all integers. It's very famous. We know what the operator norm of this nth partial Fourier sum. That is just the L1 norm of the Dirichlet kernel, and that grows like log n. So in this case, we have the classical Lebesgue constants, and they grow in n, but they grow logarithmically. Okay, so let me organize these boards a little bit better. Now, how do we get our hands on this problem? There's a nice little proposition. We go through this slowly. So this is just saying that a set is a uniform convergence set, a set of uniform convergence, if and only if these numbers, these Lebesgue constants, are uniformly bounded in capital N. They don't grow. So I take E to be all integers. I know Lebesgue constant, classical Lebesgue constant grows like log n, so it's not uniformly bounded in. And that just means that the set of all integers is not a set of uniform convergences. We all know there are continuous functions that do not have uniformly convergent Fourier series. Right, so let me get the proof. Okay, so how do we do this? So let's go in one direction first. Let's suppose that suppose E is uniformly convergent, is a UC set. That means every function that's Fourier supported in E automatically has a uniformly convergent Fourier series. Then I know that for every function with Fourier supported in E, it has a uniformly convergent Fourier series, and in particular, so these guys are converging in the L infinity norm. So if I take the L infinity norm of these guys, fixing F and taking the sup in N, this is necessarily continuous. Okay. And these guys are about a family. These S's form a family of bounded linear operators. I know on each element in this Banach space is uniformly controlled. And now I can even control it uniformly in F. This is the uniform boundedness principle. So the uniform boundedness principle And this is probably a stupid thing, I should probably definitely say, especially in this audience, this is the Banach-Steinhaus principle. Implies that in fact, I get that this is, I can upgrade this to an operator norm. Okay, and n, which is precisely these Lebesgue constants. And so this has to be. All right. Now, what about the other directions? The other directions which were classical. Okay, so let me outline that. This is, I don't know what we tend to call this the 3 epsilon lemma. Okay, so let's suppose, I'm going to suppose that these numbers, define them, I'll take the supremum of these numbers, the Lebesgue constants, suppose this is finite. And so now let me take, so let's let f be a continuous function that's Fourier supported in U. I need to show you now that automatically it has a uniformly convergent Fourier series. Okay, so then of course I need to get a sequence that gets close to f, that has all of which are still in this set, and all of which have uniformly convergent Fourier series. That's just taking the fair means. So if I take an of f, for instance, to be the arithmetic mean of okay, so I know that's convolution with the fair kernel, so these guys uniformly approximate f. Okay, and of course, if f was Fourier supported in E, all of these guys are Fourier supported in E as well. Okay, and so we know that this classical result, that these guys converge uniformly to f. All right, now let's see if I can squeeze everything in here. Now I'm given an epsilon, small epsilon, and all I want to do is now I want to show that the partial sums of f form a Cauchy sequence. I want to show that this converges in the L infinity norm. Okay, and since I'm dealing with a Banach space, it suffices to check that this is in fact a Cauchy sequence. And so I have so let me just add and subtract. The usual sort of thing I'm going to take is one of my functions. I'll take some arithmetic mean of some fair mean of f. So I'll call that g. So I'm just going to look at f of f minus g, plus I'm going to look at the nth partial sum of g minus the nth partial sum of g. I know that this is going to get arbitrarily small as m and n go to infinity because they're trigonometric polynomials. So in fact, this is 0 for large m and n. And then finally, I have the nth partial sum of f minus, so g minus f. Okay, the usual thing. So I have this as the L infinity norm. Right, so I use the triangle inequality. This guy I can uniformly bound. Remember, everything is in this space of continuous functions that are Fourier supported. So the operator norm is bounded by this LE. So I have twice of these guys times f minus g and L infinity, plus I have this guy here, Sm of g minus Sn of g, but this is 0 for large m and n. G is going to be taken to be one of these fair means of f. And this guy is uniformly bounded by assumption. And I'm now approximating my f by one of these guys, which I can make a small side arc. So if you do this carefully, you'll get everything less than epsilon by choosing each 3 terms to be less than epsilon over 3. The famous epsilon over 3 argument. Okay. Great. Right. Okay, let's go back to the squares. Okay. So do I have any more room here? Maybe a little bit more room. For the moment, but let's consider now. Let's consider the squares. And now let's consider and let's look at this function, trigonometric sum. I'm going to sum e to the 2 pi I. This is a nice trick I am doing here. This is, of course, the heart of the Archipel-Volkov argument. It took a long time to sort of pin down. So I'm going to shift. I'm going to sum n symmetrically from minus n to capital N. I'll use the notation dash because I don't want to sum n equals 0. That doesn't make sense here. And I shift everything and I'm going to square it t. Okay, so this guy is a trigonometric polynomial. Clearly, it's clearly a continuous function that is Fourier supported in the squares. So where are the frequencies? Let's check. So this is a finite number of frequencies. So where are the frequencies of Fn lie? Because I want to take its partial sums. It's already just a trigonometric polynomial. And when I take the nth partial sum or some Fourier partial sum, all I'm doing is restricting the Fourier coefficients to be up to capital N. So the frequencies lie in, let's see, where are they? Well, they start at 0, and then they go along the squares, and so on. And then they get up to, it looks like 4n squared. Okay. So these are where so I've shifted these things. And now I want to cut it. I want to reduce it. And but I want to try to do it. I want to take a particular Fourier partial sum of this guy, because I don't, so there's this, by the way, this is looking like this is an oscillatory integral, it's just discrete. It's an exponential sum with this quadratic oscillation against a discrete Hilbert transform amplitude. Where have we seen that before? It's all part of the previous lectures. So this is a discrete version, so you can sort of see where the connections are going to come from. And what we want to do here is destroy. I want to take a Fourier partial sum to destroy the cancellation of 1 over n. I'm summing symmetrically. So as many positive n's as there are negative n's. So let me kill off all the positive n's. So how do I do that? I'm going to only let the negative n survive. I want to go from minus n to minus 1. So when n is minus 1, when it's minus n, I get 0. Then I'm going to go all the way up to, when n is minus 1, I'm going to the frequency n minus 1 squared. So somewhere in the middle here, somewhere in the middle. I want to cut those off. So I'm going to take the Fourier partial sum up to frequencies from 0, but not up to 4n squared, but up to n minus 1 squared. Okay, so go up to n minus 1 squared. And so all I have is, I've just chopped things off so that only the negative little n survive. So this is going from n equals little n from minus n up to minus 1, e to the 2 pi I n plus capital N squared t over n. Now there's no more cancellation. And therefore, now you see, now let's look at the partial sum squared of Fn at 0. Now let me plug in 0. So I'm summing 1 over n. I'm not summing positive n. I'm just summing 1 over n from 1 to capital N with a negative sign. That's just log n. So this guy, an absolute value, is just about log n. On the other hand, this is at most this partial sum on this particular trigonometric polynomial is L-infinity. That's just one value. So what is but this guy, now this is controlled by the operator norm of this guy. Okay, so that is by definition, this is this constant along the squares at the order n minus 1 squared. Okay, of the L infinity norm of Fn. Okay, and this guy I want to show is getting large. Okay, so the heart of the matter, notice this is growing like log n on the left hand side. So if I can control, of course, this can grow. But the observation, this has the cancellation now, and it has additional cancellation coming from the oscillation. And so the main estimate now, the main observation, and this is the main bound of what is the archetype. So the main bound is of Archetype and Skolkoff. They show that the supreme of Fn and L infinity is finite. Okay, so they show that when I take the absolute value here, okay, and I take the supreme, that it's uniformly bounded in capital N and in T. T is the infinity group. And so this implies that this is uniformly bounded. This implies that this guy has to grow at least like the squares. At least like log n. And so they're not uniformly bounded. So by our proposition, it says that the squares is not a set of uniform conversions. So there exist continuous functions that are Fourier supported along the squares that does not have a uniformly convergent Fourier series. Okay? Now I want to write this out. And but this is a good time. Let's take a break. Okay. I want to rub off all the boards and I want to write down this estimate and look at it. Okay. And see if there are connections that make with the rest of this course. Okay. So talk among yourselves. Guys are much better behaved than my computer science students. Grab the final grab me where there. Okay, so let me write again this main bound of Archetype and Skolkoff. So I'm going to write out this quadratic phase. So what they actually proved is that I sum symmetrically. I'm not going to sum n equals 0. I have e to the 2 pi I, and then I have this, I have n squared times t, plus I'm going to have a lower n, and times with this capital N. But let me actually just write this. Let me put this on this side, Tn squared plus an Sn, 1 over n. Okay, so really there were only two parameters, capital N and T, but I had this quadratic phase and just multiplying out. So what they really proved was that I have this quadratic polynomial. Naturally, these are variables that live on the circle. So these are elements of the unit circle, and I wanted, they proved a uniform bound. They took the supremum in N and the supremum in S and T think of a line on a circle, and they show that this is that's the mean. Looks kind of similar. I just want to, that's what we've been talking about. I had e to the 2 pi of some, I had some phase function, wasn't as simple as this quadratic. And it had some parameters in the phase, and I was summing things. Here I'm summing a truncation against this Hilbert, discrete Hilbert transform now, singularity. And we still get the supermodel. So they used a sledgehammer. It's safe to say that Vinogradov is a sledgehammer himself. So they use very powerful global estimates of Vinogradov's and his theory of trigonometric sums to actually get this bound. But it has this nice application. Right. Okay. Connections. Let's go to the theme. Let's finish with the theme of these lectures. Let's go to connections with Calderón-Zygmund theory. So here I'm going to look. So this was, we have to go back to about 1986, 1987. Note the, I didn't write this one. This was result in about 1988, with maybe 87, 88, but exactly at the same time. Guido Weiss wanted to understand. So he was working with a rapid question on transference, and they were looking at group actions on amenable groups and trying to transfer estimates from one setting to another, and in particular the setting of the integers. And so, as we all know, that when you ever have a Calderón-Zygmund kernel, okay, let me write the classical one, the Hilbert transform. Just use this one. So I'm integrating on the principal value convolution. I'm convolving against the principal value distribution 1 over t along the real line. That's the classical one. Of course, I could even do this in Rn. I have convolution now, but with respect to some classical Calderón-Zygmund kernel here. And in this setting, it's quite well known that you can transfer boundedness, LP bounds, back and forth with the discrete Hilbert transform. So right, this is f of m minus n over n, and I'm summing here n over all the integers. But again, I'll only sum over. So this is, all right, this is hd of f of evaluated. Now these are functions on the integers, so we can go back and forth. Okay, so this goes back to papers of Hardy and Littlewood back in the early 1930s. In fact, you can do this not for these integral transforms, but also for the maximal functions. And so, however, we considered this. Here is a result that we've looked at. This is this parabolic. This is this Hilbert transform along a parabola. This is an important sort of singular integral operator where we try to understand Calderón-Zygmund theory with respect to parabolic dilations. I look at f of x minus t, y minus t squared, dt over t. This is again taken integrated over the real line. So we have this long history. We know that this is bounded on LP. It took us a while. LP of R2, 1 less than p less than infinity. Okay, so that's Eli Stein and all of his collaborators, Nestor Riviere, Alex Nagel, and so on, that got it here. And that was but is it we type 1, by the way? We don't know. Interestingly. Still an open problem, despite the efforts of many people. Bourdain tried hard at one time in the 80s to prove this. Terry Cow at one time tried to prove this. So good people, I would say. And we still don't know. But the basic result is LP now. Okay, so that's so It's natural. So Guido was, looking at this transference on immutable groups, and he knew that sine that was a well-known central object. This Hilbert transform along the parabola, and we have an LP theory for that. So Guido asked sine, what about? So Guido asked Eli, again, about 88 or 87, maybe 86, I don't know. I was told the story several times. I don't know exactly the conversation, but it's what about the discrete version? What about the discrete version of this Hilbert transform along a parabola? So now I'm looking at f of m minus k n minus k squared. I'm dividing by k. I'm summing over all the integers k, but not k equals 0. Okay, is this bounded on LP of the 2? So we asked Eli didn't know. No, that's an interesting question. Okay, so let's look at L2, of course, first. That's where you started. That's where we started with this guy. If you remember, it had the nice little history that I looked at the multiplier that was the oscillatory integral. I had this oscillation together with this Hilbert transform singularity. And we wanted uniformity as a multiplier. Okay, that was the actual, when it was perfectly the square, that was Eugene Clem's PhD thesis. And what do I do here? Okay, so again, I have a multiplier. This is a multiplier, so on L2, I want to look at the corresponding multiplier. This is going to be now a function of periodic variables. And so I simply get the sum over the integers. And okay, now this is a little bit delicate now because it's not clear whether the sum converges or not. Okay. But it does. I would the okay, it's not clear at all at this stage whether this is makes sense, but this defines a function on the 2 torus. And the question is this a bounded function or a function on the 2 torus? That's just L2. So again, I want to stress it is one of these objects we're looking at in this course. Oscillatory integrals with a phase, just a simple polynomial phase, integrated against the Hilbert transform singularity. And then Eli was very proud of this. He discovered that in fact, you can use Carlos's theorem. This is the calculation of Eli, and around that time that you can use Carlos's theorem, the famous one, the pointwise convergence of Fourier series on L2. We can use that theorem in a clever way to show that this is indeed bounded. Okay. He really liked this. And he was invited to give a seminar about this time, 1988, 1989, to Chicago. He was invited to Chicago to give a seminar, and Carlson was visiting Chicago. And he said, oh, this is going to be great. I have this wonderful application of the famous Carlson theorem to answer this question of Guido Weitz. So he went to Chicago. He gave the seminar. Carlson was in the audience. And Carlson said, oh, wait a minute. I seem to have seen this sum before. It's in some email of mine. Let me go back to UCLA and let me try to dig that out. So he goes back to UCLA. Wait a minute, look at this top left. I think you've made the connection. It looks kind of similar. I've changed a couple of letters on you. They're the same. Exactly the same. Okay. So again, at the heart of the matter, one is coming from Calderón-Zygmund theory, the other one's coming from this old problem of Ilyánov from the 1950s. At the heart of the matter is exactly the same. Bound. Okay. So Carlson had this email from Arkhipov and Skolkov saying that they were able to prove this thing. And so he told Eli, that's known. Well, in fact, it was about the same time. Didn't really please Eli too much. However, so he was a bit upset about that. But nevertheless, the point is This bound is the end of the story for this problem. It solves the problem of the event. Okay, it's much more general. They can use Vinogradov's estimate if we replace n squared by n cubed. So you can get that the cubes or any polynomial sequences, these are never going to be sets of uniform convergence. Okay, so, but this is not the end of the story. This is not the end. This is the beginning of the story. I asked L2, what do I ask after that? Once you know L2, then you want to know, come on, LP. So this is the beginning of the story. So you want to know, is this discrete Hilbert transform bounded on LP? And that's what we're on. Okay. And that is true. First of all, some work of Stein and Steve Wanger, and then with some help with Ionescu, better Ionescu. So I'll just contribute this to this threesome. They proved that this is bound on LP for all p between 1 and infinity. Okay? So what you need to do is you cannot just use this Vinogradov as a sledgehammer to understand this one. You need to understand it as an LP multiplier. So they went back, and I had planned to use 4 more days to show you it was wonderful how you analyze this thing using the circle method. It's a natural way. They went into developing, combining ideas from harmonic analysis and from analytic number theory to analyze this in a very natural way. And they see this as an LP multiplier. They answer this question in the affirmative. Okay. So it's kind of a, but question is this weak type 1-1? To my knowledge, I think it's not. The corresponding maximal function is also known to be bounded. This is actually work of Bourgain on an all LP, little LP for p between 1 and infinity. It left open, and it turns out to be false to be weak type 1-1. It's not weak type 1-1. Okay, so I'm not so sure if that analysis, it should be true. This would be, and I've asked this question to people, and one should be able to show that this is not weak type 1-1 as well. So I'll leave that. I don't know who wants this problem. Okay, so I'll leave that to someone here. You should go through and check this beautiful annals paper of who are those people that yes, they proved that this maximal function was actually not weak type 1-1. Yeah, this guy Molden at University of North Texas. And Volska is for where is he? You don't know where he is, okay. Okay. Anyway. Now. So I'm finished. Okay. I just gonna just say, leave it to you guys. Obviously, what about higher dimensions? With these connections, the point is now, okay, you can develop this from this Calderón-Zygmund perspective, and that's very rich. But now you can start to ask, wait a minute, let's go back. I have this connection with this old problem with Ilianov about spectral sets of integers. And when are they sets of uniform convergence? Well, what about spectral sets in lattice points? Z2, what about using the argument of Skolkov and Arkhipov? You're going to then look at trigonometric sums. You're going to look at trigonometric sums that are 2-parameter, the double Hilbert transform with a polynomial phase. And you're going to want to know when that is bounded or not. And that we've already discussed in the continuous setting. And the answer is sometimes yes, sometimes no. It depends on the Newton diagram and the vertices, whether they have the parity of the vertices. And the same thing's going to happen here, I'm sure. So this is a whole avenue to explore, and I'm just going to leave that to you guys to think about. And so, thanks for listening.
Yes. Is it that the discrete boundary to the discrete Hilbert transform along the parabola implies something for the continuous one, or?
Sorry?
If you know, for example, that the discrete Hilbert transform on the parabola is bounded, then you prove just using this fact that the continuous one is, or
No.
no? It's not.
This is what Guido was stuck on. Couldn't see this implication.
But which one? The one from discrete to continuous, or?
Either one.
Either one. Okay.
It's a little bit subtle, right? I mean, if you think of how you do this for classical Calderón-Zygmund, it's not so hard how you take a function on R or Rn and approximate it with functions on the lattice points, and the differences are quite well controlled. Here, it's that these things are convolution now with the distribution along a lower dimensional variety. Right, so this now you discretize this thing, and so this simple comparison that one has in these classical settings just don't seem to work, and this is why Guido came to this and thought, is this even known whether these discrete operators are bounded or not? And that's when he asked Eli. And so Eli, of course, spent a lot of his time later in the latter part of his life investigating all of this. And again, extending there's a whole big theory, not for these guys. By the way, I should have mentioned that if you want to show that this is a bounded function, what you do is you truncate this from k equals minus n to capital N, and you show that it's uniformly in capital N and beta and size. So B is exactly the same problem that you're dealing with up there. But now so in the context of Calderón-Zygmund theory, it's natural to start to consider these guys in higher dimensions, maybe not along the curve, but along lower dimensional varieties. The varieties could change in the dimension. And so you have a whole slew of discrete integral operators, all of which we know the continuous analog, and all have been worked out through the 70s and the 80s and the 90s. These singular radon transforms, these maximal radon transforms, you can look at their discrete analogs and you can try to prove all of that. But we don't know how to, so showing that one is not weak type 1-1 doesn't necessarily say anything about the other one being weak type 1-1 or not. But this one I suspect is certainly not weak type 1-1, although this one I expect is weak type 1-1, although I failed to prove it.
Please. So, in the definition of Sidon set,
Yes.
any subset of Sidon set will be again a Sidon set. Any subset of Sidon set will be again a Sidon set.
Yes.
So, my question is that, for example, take E equal to the power k Sidon set. Is there any investigation that if you keep increasing the elements on that set, how much can you go that that set will not be Sidon set anymore?
How much? Sorry.
Like if I keep increasing the elements on the 2 to the power k set.
Yeah, there are some obstructions that you come into just on density grounds alone. That you can't go to a certain extent. Okay, so this is sort of part of the so by necessity, Sidon sets have to be sparse. And if you go beyond sort of threshold of that sparsity, you're no longer a Sidon set.
Okay, so this is done for any general Sidon set, not just 2 to the power k set. Like for any set.
Yeah, for any Sidon set, there's all of these arithmetic properties that they all share in common. And that was Rudin's big program, was to try to see, is it maybe we can characterize these sets. I mean, just looking at these particular arithmetic properties, any set that has this arithmetic property isn't necessarily a Sidon set. That was the big tantalizing problem that PZA eventually solved.
Questions? Okay, there's
So you showed us before this example of UC set that it's not a Sidon set.
Yeah.
So if I take the two Sidon sets and take their additive sum, do I get a UC set?
Yes. That's a good exercise.
no questions.
That's a good question.
So now it's time to
Finish.
stand. Thanks for the nice lecture here last week as well in Edinburgh. Thank you very much. It was very, very instructive and very nice to attend the lectures. So let's